Recording in progress. Welcome to Lecture 6. Today we graduate to materials. We get out of flat gray and we move into the world today of reflectivity, roughness, and some color. Finally, color is actually the last thing that we worry about adding. Why? Because most people are distracted by color and really shiny stuff. So we work on the material properties first, which are how reflective is it and how smooth or rough is the surface. That will define the type of material we're looking at. Then we add a little color. Color is kind of the last thing we add in. That's like the finishing touches. All right, so today, project 6, broken out into 2 lectures, 2 labs. Like I said, today, actually, let's just. Today we are doing reflectivity. And Monday, which is lecture 7, we are doing transparency. Can't write. Transparency, transmission, glass, liquids, anything that's clear that we can see through, or clear-ish that we can see through. All right, so a few downloads for you. You're going to be using, don't forget, Project 5 now is Project 6. So make a copy of your whole Maya project folder from Project 5. Make a copy, rename it 6. This way you've got a whole separate set of files and you're not working on the same one that you did in lighting, because if anything corrupts in the materials, you'll have nothing to fall back on. So take your project 5, the interior, take your project 5, the exterior, copy those, change the name, make them project 6. We're using the lighting that is already done. The only thing we're not doing from project 5 is the MyComp. There's plenty to do here. All right, so a few downloads for you. There is a Lecture 6 demo file. It's basically a very simple scene. It's got lights in it. We're interested in playing around and trying to get a few simple material properties to get you started. We've also got reference for the bread, which is right here. And for the interior, there is reference for the thermos, which is sitting on the table. It's basically a brushed metal thermal container, similar to the one that I always carry, except that it is silver instead of color. And we're also going to talk about what type of metal this is. It is brushed. What makes it brushed? What makes it special than most other normal materials? That's what we're going to talk about. All right. Anybody have any questions from last time? Everybody good about Zoom? Questions? Jonathan's good. Amber's okay. Thank you. All right. So next week, Tuesdays, Thursdays, I'll have office hours in Discord from 10 to 4. Frank, Ari will be back next week. She will be also manning Discord and labs next week. And One of them will be doing the Thursday open lab from 1 to 5. All right, important note about materials. So a lot of times people think, oh, materials, I'll just go into substance and use substance materials. We had a little bit of discussion about this before, because anything in substance, while it may be a material, in order to get it out of substance and into another program, what do you have to do? Have you guys done any of this for Unreal or Maya? Yeah, you have to turn it into a map. So basically you have to export them. And it's usually going to be something like, maybe a spec map, a metal map, a roughness map, a normal map, a height map. It might even be an ambient occlusion. Depends on what you're exporting. So that's why we want to specifically state that we are not using substance for this portion of class. We will be using it when we get to texturing, but it's not going to be the only thing we use to texture, because it doesn't need to be. So we're also not going to be using pre-made or preset textures. All materials need to be made from scratch using the AI standard surface. So no maps at all. All reference that you guys will start to gather for Project 6 is to be used for what we call look development, which is basically you are getting an object that you want to make look like the reference in your scene file. So for example, you have a plastic container in your scene file. Well, you get reference. Maybe you get reference of something like this. And what should your reference tell you? Well, first off, the reference should tell you how does it respond to light in an environment. The worst kind of reference you can find to use is something that's got a pure white background, because it does not tell you where light's coming from, how it responds to the environment. It really gives you a false sense of reality. It's like magical matrix floating backgrounds. So your look development will also tell you how reflective is it? How shiny is it? Can I see some of the environment in it? Can I not? Also, it'll tell you how rough it is. If something is super smooth, you'll be able to see a lot more detail. If it's rough, you'll be able to see some detail, but the reflections may look hazy or blurry. And then finally, what color is it? Then when we get into project or lecture 7, we're going to start to talk about what makes this different from this. What makes air different from a normal material, water, liquid, and here we have alcohol, and this is a plastic bottle. What makes this look different than glass? What makes it look different than the liquid that is inside of it? All of those properties are what our look development will tell us, plus what we learn about how to make that stuff in Arnold. It's not really difficult, but it is detail work, which is no different than sketching. Because isn't sketching or drawing or painting, isn't that all about detail? Sculpting, detail. Work, coarse, big changes down to the little refinements. We do the same thing in lighting. We do the same thing in materials. We get the general amount of reflectivity we think is there. We add a little bit of roughness if there is any. And then we might add some color. And we see what it looks like in our environment when we render, when light hits it. Does that make sense? Questions? Okay. So today, like I said, reflectivity, sometimes called specularity, depending on basically the 3D application you're using, and then roughness. We're also going to get into this thing called anisotropy, which is basically brushed metal. We're going to get into this BRDF, which is also PBR materials, if anybody's familiar with that from gaming, physically based rendering materials. They are basically sort of the same thing. PBR is real time. BRDF is software where we have a lot more time to calculate something. There will also be, in addition to Project 6, there will be a discussion that's topical about materials, and also a research discussion component, which is 6.3. This is what we're going to go over right now. Only because I want you guys to get a heads up about it so you can start looking for a topic and a place to find the article that interests you. All right, so the research discussion is in 6.3. Basically, you want to try to find an article that interests you, that is industry related, meaning it is what drives you, what got you up in the morning to come to school, why did you come to Full Sail, what are you passionate about as far as 3D art goes. Doesn't matter whether it's gaming, doesn't matter whether it's animation or film or TV. It really doesn't matter. It's all related. All right, so this is going to be a lot more formal than the other discussions. Since it is a research discussion, we have certain parameters. The first is you must have a citation. Okay, we use APA, which you guys should be familiar with, from what I understand. American Psychological Association, it's used by most universities. It's just a format for the article you read, the author, the journal or source that it came from, and page length or page range. You're going to provide a link to the article. The link, though, is going to be very specific. If you are using, depending on the source you use. Let's go back to that part. So I have a couple of sources here. So if you use EBSCO, Full Sail has a connection to, basically, it's a pool of resources from other universities and research facilities. It's basically people who do research, who do development, who want industry, whatever industry that happens to be. If they want to have updated information in news, they will usually use something like EBSCO. EBSCO happens to be, educational based. If you use EBSCO, EBSCO has some tools in its little search app on the web when you first log in that will give you things like APA citation. It'll give you things like what's called a permalink, which allows you to copy the source from EBSCO, give it to somebody who is not logged into EBSCO, and they will be able to read that article. If you just copy the URL out of your browser in EBSCO, as soon as you exit the session, that link is no good. We also have a couple of actual online journals. One is called Game Developer, used to be called Gamasutra, And the other is Game Studies. It's an international journal of computer game research. A lot more formal than Game Developer. But if you are in game art and you're not familiar with Game Developer, you should be. It's a really good source of information. They do game reviews. They do interviews with the people who make games. They do industry trends. One of the big things that they do occasionally is when a game comes out after a few months, they will do what is called a postmortem, which is basically they'll sit down with the developers and the artists and go, okay, what went right? What went wrong? What would you do? What would you do again? What would you not do? Basically, lessons learned. So really good information. All right, and then you are going to discuss the article. And this is not your typical, give me a recap of the article. Discuss the article as it relates to you, or the you component. Getting just a dry recap of the article is actually not of much value unless you're trying to abbreviate it for somebody. But when you're trying to share information, you usually get excited about it, for good or bad, and you usually can relate the article or the source or the information you're trying to give as it filters through you. And that's really what I want. I want to be able to get how you related to the article, why you thought it was important, why you thought it was relevant. Maybe you didn't like it, maybe you didn't find it relevant. That's all valid information. Does that make sense? So if you have any questions, please feel free to ask. All right, so if you use EBSCO, they will have something along the lines of this. After you do your search, it'll come up with a whole list of things. Click on one of them that you think interests you. It'll take you to some place like this, usually an area like this. And they'll either give you a PDF or an HTML text. Doesn't matter which one you use. It's all good. There's a citation button. Click that. It'll ask you what format you want to use. You just select APA. Down under permalink, click that. That is what you copy and paste in your discussion underneath the citation. Or, you send it to a friend, whatever you want to do. Now, if you give me an article and you didn't use the cite or the permalink button in EBSCO, this is what I get. So I need to be able to verify the article, because I will go to the article, and a lot of times I will go download it if I think it's interesting or I haven't read it before and I like it. I will definitely look at it. So sometimes in EBSCO, when you click on the link and it takes you to what you think is the article, sometimes it will take you to basically an overview, which will include what is called an abstract. An abstract is basically a very formal introduction to the paper or research topic that is, being posted. Now, it's got to have the full article, not the abstract. A paragraph is not going to cut it. All right, so when all the stars align, you have citation, you have a link that takes you to an actual article, and then it could either be HTML, could be a PDF out of a journal. It doesn't really matter. So game developer, very simple to find. Come on, I don't want game developer salary. Just give me game developer. There we go. So there are tons of sections. There's connections, blogs. The thing you have to worry about blogs is that it's just somebody's opinion. However, when you are connected to a site that's got some credibility, a blog is a good thing because then it's an actual discussion. But I highly recommend the article. So take a look here, peruse around. You got all kinds of disciplines. A lot of people choose art. So whatever you happen to want to choose. And like I said, there is also game studies, which is pretty good too. All right, questions? Anybody have questions in Zoom? No? Okay. Thank you. All right. So let's go and start to talk about materials. So when we first started talking about lighting, we talked about this type of reflection. Anybody remember what it was called? Diffuse. Good. So kind of a refresher, why is it diffuse? Well, light hits it just like it does any other surface. The surface has microscopic irregularities right here, represented by this little graphic. Light rays come in. Light rays will usually come in some kind of organized pattern, unless they are just pure bounce light. But they will come in, they will hit that surface, and they will start to bounce around in all different directions. Why? Because all those microscopic irregularities will take that light ray off its path. So it will start to scatter in all different directions, creating kind of an even blanket across the surface, which we call a diffuse reflection or a diffuse material. Now, when you have a much smoother surface, like a mirror, very hard plastic, chrome, kind of, I don't know, nickel-plated chrome, whatever you happen to have that's a hard, smooth surface that's been treated, then you will have light rays bouncing off in an organized fashion. So the incoming light is called the angle of incidence. It bounces off of the surface. That is the angle of reflection. In CG, we track all of this based off of the normal on the surface. You guys know about surface normals from modeling, right? Every single polygon face has a normal. And that normal will be 90 degrees or perpendicular from the surface. So when you have a light ray coming in, it'll hit the surface. Immediately, the surface will be measured by whatever you are measuring, whether it's a camera ray, whether it's a light ray, whether it's a particle, whether it is a rendering sample. It's all measured off of that, the angle that it hits to the angle of the surface normal. So you have something coming in, it bounces off. So the angle of incidence and the angle of reflection. Surface normals used for a lot, just, a lot outside of modeling. When we get into working with height maps, they're all going to be based on where the normal is to the camera. And that's really how all of this is measured. Remember when we were trying to figure out that compass of light, we're always looking at the subject and the relationship of camera to subject. And then where does the light hit based on that? This is kind of the same thing, except the subject is basically the normal. The normal comes in, gets the information, sends it to the renderer. Does that make sense? So let me just pull up Maya real quick. And I'm just going to create a simple sphere and a camera. Sphere, create camera. Let's go into top view. All right, so if I select the surface, go to display, polygons, face normals. Let's go to wireframe. All right, so when the camera is looking directly at the surface, this is called a 0-degree angle, just like the camera directly looking at the subject. So we have a little compass that's very similar to the compass of lighting. So we got 90 degrees left, 90 degrees right. And honestly, since we're dealing with visibility, we're not really concerned with what the camera can't see. So when we look at something, and this goes for us and also CG, when we look at something directly, we see one level of reflectivity. When we look at something at a glancing angle, which could be like 90, even 45 degrees, as we start to see the edges of an object up to 90 degrees, it becomes very, very reflective. So a lot of times you will look directly at something, not see reflectivity. Take, for example, our walls. Stand in front of them and look at them. They look very flat. However, start to come around to the side and you can start to see a little bit of reflectivity from the light in the room. And I encourage you, get up and take a look. So if I stand over here, sorry everybody in Zoom. If I stand here and look at this, it looks very flat. But as soon as I start to look at it at more of an angle, well, I can see some reflections from the ceiling. I can see a little bit of reflectivity from the light. I'm coming almost around to 45 degrees from where I was. We're at 90 degrees. So right now I'm at 0. If I start to come over here, I can start to see reflectivity. By the time I get almost 90 degrees, it's much more reflective than it was when I looked at it directly. That is called a Fresnel reflection. F-R-E-S-N-E-L. So as something, or as our viewing angle changes, we start to see more reflectivity. So some of you may have heard of Fresnel before. The S is silent. They use Fresnel lenses all the time in lighting to kind of disperse light naturally. They use them in car headlights. They use them a lot in flashlight coverings. But what we're interested in as far as the Fresnel effect goes is that we see more reflectivity when our viewing angle changes from 0 to 90 degrees. So bear with me on this. Most of you have probably been to the ocean, a lake, or a river, right? If you go down to the ocean, and I'll use the ocean since we're in Florida, right? You go down, stick your feet in the water at the edge of the shore, look straight down. You can usually see through the water and see your feet, right? As you start to pick your head up, the water starts to get, well, it gets deeper, but you start to see less transparency. You can no longer really see into the water much. You start to see a lot more reflectivity because that body of water is starting to reflect more as you look out towards the horizon. So by the time you hit the horizon, it is nothing but a mirror. You're seeing reflections from the sky. Same thing if you're driving down a road, a long road, maybe it's a hot day. You look in front of the car, looks like asphalt, looks like concrete. Pick your head up. If you can take a look down towards the horizon as the road kind of disappears in the distance, the ground will start to look wetter. That's because we're looking at something as it gets more reflective way off in the distance. Does that make sense? So we have that same feature in CG. Now we call this BRDF, or bidirectional reflectance distribution function. It just means we measure something from two distinct viewing angles, and they are 0 degree, 90 degree. PBR materials in gaming use the same feature. 10 years ago, materials in games were not what they are now. Everything has gotten a lot more sophisticated. When we started getting into PBR materials in gaming, everything started to look much better. Think back like 10, 15 years ago, old school games, kind of flat. They may have had some reflectivity, but they tended to really not stand out. At the time, they were great because of what had come before, but compared to now, they are pretty dated looking. So like I said, everything is measured off of the angle of the normal. That's what keeps track of how and what hits the surface, whether it's a light ray, a camera ray, a photon, a particle, a wave. It doesn't matter what hits our surface. Questions? Why is all this important? Well, glad you asked. Because when you start to get look development, which is basically a reference of an object that you would like to recreate in your scene, you're going to be looking at it from a particular point of view. And what you want to do is set your material up from that particular point of view so you can match it as close as possible. And then take a look at it in the render view, like the camera angle that the final render is done in, because a lot of times they are going to be different. So you want to try to match it based on your viewing angle, then see what it looks like in your scene at your camera angle. Close up, long shot, doesn't matter which one. All right, so with the ability to have a lot smoother surface, more organized light rays as they come off, we start to see environment reflections. Why? Because we are getting, remember, everything is a result of reflectivity. Light hits a surface, bounces off of it. When light bounces off a surface in a uniform direction, well, all the other surfaces that are bouncing light back to us will show up in the environment in the reflection. Remember, everything we see in the real world is a result of reflectivity. I see this object because light is hitting it. My retinas are picking up the different colors. And the viewing angle I look at is going to determine how it looks to me at a particular point in time. Now, in addition, when you have organized light rays, you also have the ability to see direct light sources in your reflections. All right, so direct light sources right here, you guys should be able to see. Let me make this a little bigger. Spotlight. Yeah, continue. There we go. All right, so you can see this is a pretty clear, smooth surface, mostly, besides the fingerprints. And you can see a lot of reflectivity. Take a look at the back of my phone. Still pretty clear, although a little wobbly, a little wavy, and a little blurry. That's because this is a slightly rougher surface than the glass front of my phone. This object right here. So here on the edges at the bottom, a little bit of a harder surface. You can see a little more detailed reflection here, but notice the top part where it's rougher. Look what happens. That was nice and clear. This is all blurry. That's because this portion of the material is rougher. Same thing here. You can see the areas where it's nice and smooth. I bring it down here on this label, and this label is rougher, and consequently, everything looks a little hazier and blurrier. But all the little individual light sources that we have in the room, like the projector bulb, which I don't know if I can get this to show the projector. That might be it right there, hard to tell. The projector, you can see a lot clearer, but where it is rougher, you can't. All right, how do I get back out of here? Remove spotlight. Let's go gallery. So those direct light sources will show up. Why? Because light hits that surface and finds its way into the camera or into your eye. That's why we see what are called specular direct light highlights. Makes sense? Questions? All right, so an average ordinary reflection is called an isotropic reflection. Garden variety. Isotropic simply means that no matter how I turn the object, I'm going to see the reflection the same way. So the top of this plastic container is a real good demonstration of that. It looks more or less the same. So technically, it's made up of three components. One is called the base. which would be your primary visibility color. On top of that, you'll have actual reflections. On top of that, you'll have specular highlights, direct light highlights. So we get a final reflective surface that is basically three components: visibility, color, environment reflections, specular direct light highlights, all wrapped into a nice, neat package. All right, now, when we get into talking about color, did an Unreal Fest. Unreal every year has virtual festival where they will come in and they'll have like 2 or 3 days of presentations, different topical discussions. The one that really interested me the last time was the PBR materials. I mean, I know about PBR materials, but I always like to go to these sessions to find out more because they're always improving the material design, especially in Unreal. So they were talking about PBR materials, and they said the one thing that artists in general in the beginning make a mistake with is they see white, they assign pure white. They see black, they assign pure black. The problem is it looks artificial, it looks CG. Nothing is pure white in the real world. Nothing is pure black. They're all very light gray or very dark gray. Even things that we think of as being black. So for example, they said the most common thing is people see like black charcoal, really dark charcoal. They'll see like super dark areas. They will immediately throw in pure black. So what they did was they took a bunch of photos of really dark materials like charcoal. They did some fabrics. They did dark shadowy areas, which really aren't the same thing as materials, but they were just trying to show that there should be nothing that's pure black or pure white. So they did that. They also took some examples of snow because a couple of the guys had gone snowboarding. They took pictures that they had and they measured them in Photoshop. And they said that the average really dark area in Photoshop is roughly 0.02. 0 is absolute black. 1 is absolute white. They said, for example, the snow, really bright snow with direct sunlight, taken with a good camera, taken into Photoshop, the white was between 0.81 and 0.9. And they said, limit your values to be under 1 and to be over 0. So everybody says, I say, what color is that? Everybody says black. No, it's going to be really dark gray. What color is that? It's white. No, it's going to be really light gray. You need to think that way because you want to get as much contrast as you can. And if you limit yourself by going absolute 0, absolute black, you got nowhere to go. Just like in art. You're doing a pencil sketch, you really want to refine the shading in it. You're going to have very few areas that are going to be absolute black and very few areas are going to be absolute white, the color of the paper, right? You really want to have different tones in there so you can bring out the depth. So keep that in mind. Questions? All right. And let's talk about, let me get my prop. All right, so for this next part, let's talk a little bit about objects that we see. So sitting at my desk, I took my mouse that I have right here. It's got a very hard, smooth plastic back to it. It's got a button area, and it's got rubber grip on the side. So I had them in front. In fact, I used my pen holder as a base for it. And I had a really dark gray hat sitting back there. So the hat will establish as being diffuse. It's fabric. The thing about a diffuse material is all those little fibers from the fabric send light in all different directions. So this is diffuse. Everything else is more or less not diffuse. So the back of my mouse, this area right here. Should be able to see lots of reflections. You can really see a lot of detail. This, even though it looks really hard, really smooth, this would not really be perfectly smooth. No matter how smooth something is or polished, you can zoom in with a microscope and find irregularities. But this would be considered to be a very low roughness surface. Now, roughness is sometimes also termed glossiness. Sometimes you will see a high glossy surface, which means it's smooth. Low glossy surface means it's rough. And a lot of times, people will, or software packages will bundle them into spec gloss, metallic roughness, which you probably have heard before. Especially in Substance, they kind of have those models. But ideally, roughness is really the terminology we want to use. Glossiness, yeah, not everybody understands how you're using glossy. So think of low roughness as a hard, smooth surface. Sharp, detailed reflections for the most part. They're not going to be perfectly razor sharp. They may have a little bit of softness to them. So the top of my mouse, this whole button area right here, you can see what it does to the light. So I have a rectangular light on my desk above, or I have a rectangular light above my desk. So you can see pretty sharp detail here. The mouse is in the same position. You can see that the surface itself, even though it doesn't really feel rough, it has roughness in it. So this would be considered to be kind of medium to medium high roughness. It's going to give us hazy or slight, blurry reflections. Everything is going to become a lot more impressionistic rather than being sharp detail. Soft highlights, hazy highlights, blurry reflections, however you want to think of it, that's what's happening with roughness on a surface. The light hasn't changed. The light is still reflecting the same off the surface, but the surface determines how we see it. So then we get into, on the sides, this rubbery grip. Now, the rubbery grip is going to be a lot rougher than the top mouse part. Not to the point of being diffuse, because you can see my hat up there, that's diffuse, but we have some really super soft light highlights here. We have 0 up there on my hat. So while this is a very high roughness surface, it is not to the point of being diffuse. It's not carpet, it's not fabric, it's not matte, as some people would call it. Does that make sense? So if you had a mouse in your scene, this is how you would be analyzing that mouse. It should be modeled correctly in the different parts. Now, I know when you guys learn modeling, they drill into you, build your model in parts, because all those parts in manufacturing may have different materials applied to them. Questions, comments, discussion? So let's do a quick little exercise. You guys have the flat part of your desk, and then you have those little rubber edges. Which one looks smoother? The what? Okay, so I heard the rubber edge. Why? Okay. Well, let's go take a look. So we're talking about this rubber edge right here, right? So looking at it, you would say that's glossier than the desktop.
No, close enough because of the way the light is. I can see my cord in this desk better than I can see it.
Yeah. So the thing about the desk is, if you look at it straight on, you're trying to look at reflective. But when you start to look at it in an angle, it does look a lot more reflective. That would be a perfect example of the Fresnel reflection. Looks different. And right here, yeah, you can start to see actual reflection. Here, this is, well, now, some parts of this rubber may be smoother than others from being rubbed on all the time. So students can put your arms on there, you rub it back and forth. That's going to take any of the roughness on the surface and kind of wear it down. So consequently, it could look smoother and glossier than the top. But for the most part, I would say this is probably going to be a lot rougher and lower glossy. How about the chairs? What's that?
Are you asking me?
Well, pick a part. We got, let's just do 2 parts. You got the seat back, the cushion, and you got the armrest. So do the seat backs first. So we're talking about this right here. So diffuse. Now, to tell if something is diffuse, take a look at it from all angles. Does it look the same? As you look at it from the side, does it look a little shinier? Okay, compare that to the carpet. The carpet, I would definitely say, is diffuse. All those fibers in the carpet definitely scattering light all over. The chair, I don't know. That's kind of hard because it may have the smallest amount of reflectivity in it or I should say, the smallest amount of smoothness, not quite as rough as the carpet. Yes. Yeah, it looks a lot shinier, almost kind of like our walls, actually. Our walls are sort of the same way. Semi-gloss paint on the walls. This fabric probably has been treated to be stain resistant. So consequently, it's going to have a little more, it's going to be a little harder, a little smoother. All right, good. How about the armrests? Right, top part right here. Just put your arm on. Okay, reflective. Is it perfectly smooth? What makes it rough? All right, so we're talking about texture, and really we're talking about light information. Now, texture, I would like to limit to your desktop has a texture on it. It's got a pattern, right? You can't get that with a single color. The armrests you can get with a single color. However, what we're seeing is the result of light hitting the surface. It's got minuscule indentations, kind of a sandy, rough pattern. So all the low-lying areas look darker than the top areas that look brighter. So we're seeing that pattern as a result of height variations on the chair. The color of it is fairly uniform. Does that make sense? We'll get more into that when we get into texturing, because then we're going to decide, do I need a texture to describe what I'm seeing, or can I get away with a solid color and a height map? So for example, our walls right here. Look perfectly even in color. Go up a little closer, and like most Florida walls, they have that kind of orange peel, bumpy texture on it. But you really don't notice it till you get about 5 feet away and start to come in closer. But what we're seeing is not a result of an actual pattern, color variations. We're actually seeing height variations. Did I lose people? No? Everybody good? Okay. All right. Now, when we start to talk about changing reflectivity, adding in transmission or refraction or transparency, we are talking about trying to maintain what is called a physically accurate material. Much like the physically based rendering materials in gaming. We try to maintain a 100% energy ratio on that material, meaning you can only have 100% of the energy in there. If you've got a base color and that's all you see, you got 100% in the base. For us, in the previous exercises, that was diffuse, 100% diffuse. Now we're going to start to add in reflectivity. When we add in reflectivity, before reflectivity was down here, base or diffuse was up here. When we start to add in reflectivity, guess what? We're going to steal from the diffuse. Because you can only have 100% of the energy. When you have something that's totally reflective, then you've stolen all the energy from the diffuse and made the whole object totally reflective, like a mirror or chrome. Same thing happens with transparency. Transparency will basically replace the diffuse, but transparency is not all transparent. A lot of transparent objects have reflectivity. Glasses, plastic. So you have to share the energy between transparency and refraction and reflectivity. We call that conservation of energy. You can push these materials past that point, but then you have broken their physical accuracy, and now you're getting into stylized. You may get some cool results, but they're not going to be physically accurate results. So for our purposes, we are trying to match and learn how real world objects behave so we can recreate them. Later on, feel free to break the laws of physics and do whatever you want. But as long as you know how to make the real thing, it's like drawing. You do circles, you do lines, you do shapes, 1,000 heads, 1,000 hands, you wind up doing, right? You get better and better and better, so you know how to draw a hand. Once you know how to draw a hand, guess what? You can stylize it. You can elongate the fingers, make the knuckles really big. You can do all kinds of things to it to give it that extra emphasis. All right, so we break our materials into two parts for reflectivity. We have what are called dielectric materials and what are called conductor materials. Dielectric materials are things like paper, porcelain, glass, plastic, air, rubber, wood, concrete, pretty much anything except metal. Metal, that material type is called conductor. Some software packages will have a separate, what they call artistic section, and a separate physical section. Arnold, V-Ray, they don't care about that. They mix and match the stuff. But you need to know how to make these two basic types of materials. Now, fortunately, most software packages take glass and make it its own thing. Sometimes they'll call it glass. It'll be called transmission. Sometimes it'll be called refraction. But what they've done is they've kind of removed glass from the dielectric equation, even though technically it does exist there, and made it separate because that's how we build materials. Those three main components. We've got base, diffuse, reflectivity, spec, transmission, refraction. Our energy is distributed between those three parts. All right, does that make sense? All right, so I'm going to go back. We'll come back to this again. So in Arnold, dielectric materials, the three components we use are base color. Guess what? There are your three components for making something reflective. You've got the amount of reflectivity, which technically is right here. When we say how reflective is something, right here. How rough is something? Down here. And then what color is it? Up here, color. Now, in Arnold's way, we have this extra component here called specular color. Now, I know a lot of software packages, including Substance, whenever you do spec, they always put color in there. But technically, all the color that we see in reflections is a result of the environment that is reflecting onto the surface. The exception to that is metal. And I'll explain that in a second. But for dielectric materials, specular color will always be white. You want any color in your reflections to come from the environment. Like this, I got a little blue, I got a little red, I got a little white, a little gray in there. Okay, all of that is coming from the objects themselves. Now, for metal materials, Arnold has actually a pretty simple solution. You have this control under base called metalness. Once you turn metalness up, complete reflectivity takes over. As long as you have your specular weight turned up, it will look like a reflective object. All right. Remember how I said we view things from two different viewing angles, like 0 degree and 90 degree? Well, Arnold uses the same principle here. So metalness, this is your 0 degree reflectivity. And specular weight, this is your 90 degree reflectivity. Same thing up here. This is your 0 degree color. And this is your 90 degree color, which for the most part, reflectivity is always going to be white. So metalness gets turned all the way up. The color of that metal is going to be determined by your base color. And oops, looks like I moved this. This should be down here. Oops, there we go. So your base color will determine the type of metal you have. Weight, it's always going to be 1. Color, this is where it gets gray. And I'll talk to you about that in a second. All right, so let's take a look at the metal column here under materials. So we've got steel. Let's do that. Steel. We got steel. We got aluminum. We've got iron. We've got silver. On the opposite side, we've got copper, gold, brass, bronze. Anything that we would consider to be silver or gray or even dark gray, steel, even iron, they are technically called white metals. And this one. Anything like copper, gold, silver, or gold, brass, bronze, these are what we call red metals. And they could argue, yeah, but copper, brass, bronze, they're kind of orangey. Yes. However, hear me out. Remember when we talked about the electromagnetic spectrum, we talked about our visible part of the electromagnetic spectrum. Our retinas handle red, green, and blue color, right? When all those colors are equal, we get white light. White metal is simply reflecting back even bandwidths of all red, green, and blue light. Consequently, we see white, or we see gray, or we see silver. On the other side, you've got brass, you've got bronze, you've got copper, you've got gold. They reflect back mostly orange, or mostly the red bandwidths of light that we see. That's why in metals, we see that color. because that is the bandwidth that the light reflects back. What happens to the others? Yeah, they get absorbed. So if you understand this, you will understand why we only add color in the specular section of the material when we're dealing with red metals. Otherwise, we want all our reflections to be based off of white light. Now, anybody who's interested in a little more detailed explanation, I've got a PDF in here from Flynn Scientific. They basically measure a bunch of stuff. So if you go in here, it'll say why copper is reddish in color. Honestly, this first page is a really good read, except for down here, the end of this paragraph. This is the part that scared me. And then down here, I glazed over because that's way above me. I know what it does artistically. I really appreciate what it does scientifically, but if you had stuck me in a room with a gun to my head and said, you know, analyze this and write out the equation for the electromagnetic spectrum, I'd be dead. So, but this part is pretty simple to understand. Silvery color, most metals, you're going to get equal bandwidths of white light reflecting back. You get the yellowy, orangey, reddish colors. Those are going to be the reddish bandwidths of light that are going to reflect back. So, like I said, first page, easy read. It's important to know as an artist. You may not think so, but actually it is. All right, so the technical parts. For dielectric materials, as I mentioned, base color, this is the object's color when you look at it directly. So here, blue lid, 0 degree. We would put blue in our color in the base. Specular weight. Most of the time, you start with your specular weight on many surfaces at 1. Keep it all the way up. There are a lot of occasions where we'll back it off because it's just too much. We can control that. Now, the reflectivity of it. That's all this stuff here and on the sides. That should be white except for red metals. Does that make sense? So most common objects, other than metal, what color is it? How reflective is it, which is specular weight? And then how rough is it? We'll get to roughness in a second. Actually, roughness is super simple. In Arnold, 0, no roughness at all. 1, total roughness. It does look a lot different than just the diffuse part. But most objects have a level of roughness in them. And Arnold, believe it or not, Arnold, Renderman, and V-Ray all start off with roughness at a level of 0.2, which is actually quite a bit of roughness because most objects have some type of roughness in them. Does that make sense? So when we say, how reflective is it? Start with your weight at 1. Take a look at it. Then, how rough is it? Dial in the amount of roughness. Not as much roughness here as there is here. And then we figure out color. Very light gray, bluish. We get into metal. You have a metal object. Doesn't matter how rough that metal object is, start with metalness at 1. Turn it all the way up. Base color, that is the color of your metal when you look at it directly. So for example, aluminum, or if you're in Europe, aluminium. So what color is this metal? So white, gray, silvery. So that would go into the base color. The edges of it, 90-degree reflections that we see. Notice how it's a lot more reflective up here than it is here. Let me see if I can make this bigger. When I'm doing that, I keep forgetting. So a lot more reflective up here than it is here. So light gray, silvery color. We keep our specular color at white. That's for the reflectivity of this. Now, you've got something other than red metal. This is metal, but it's got a coating on it to make it appear bluish. It's got a kind of a colored lacquer on top of it. And that is technically what's causing this. But underneath of that glossy lacquer is metal, and you can see the metallic properties. So in theory, this would still sort of be white metal-ish. Even though you've got more of the blue reflecting back than you would, this would be kind of the exception to this. Now, I don't have any copper, or I would have brought copper in. I forgot. No, I used to have a little copper airplane on my key. It fell off. Anyway, we would have color that would go into the base color. The edges for this would still be white. So metalness at 1, base color, that's going to be gray, or if it's a red metal, red. Specular weight's always going to be on the edges. That's always going to be high for metal. The specular color, if it's red metal, you need a little bit of red in that edge. Otherwise, it stays white. And roughness works the same for metal or plastic or any other surface. The default is 0.2, moderate amount of roughness. Even objects that look perfectly smooth, like the back of this mouse, that would definitely get a tiny little bit of roughness in it. All right, so that takes me to anisotropy, which is basically what this surface is. This surface is brushed metal. All right, so we talked about isotropy. I can turn the reflection here, and the reflective surface sort of looks the same, no matter how I turn it. Brushed metal, see if I can get this close enough. Brushed metal has intentional roughness grooves on it, and these are in a horizontal fashion to the object's shape and orientation. So when you have an anisotropic object, you have intentional roughness going in a direction. What it does is it forces the light to stretch perpendicular to the roughness. I have horizontal roughness. My highlight is stretched vertically. You can see it right here. If I turn the object, notice that the light does not maintain. Forgot I took a drink out of it. The object does not maintain the same orientation for the stretched light. It changes. It becomes horizontal stretch now because the roughness is now vertical. This is basically what happens with an anisotropic material, brushed metal. Take a look at full sail, bathrooms, the soap dispensers, the paper towel dispensers are usually all brushed metal. The kick plates at the bottom of the door handles here in our room, they are all brushed metal. They are all anisotropic surfaces. Does that make sense? Now, to make an anisotropic surface in Arnold, it's actually very simple. Down under the specular roughness, go past, you'll see there is a control called anisotropy, and then one underneath of it called rotation. So just like everything else in Arnold and Maya, there are little idiosyncrasies. So anisotropy basically starts at 0, it's off. You have an isotropic reflection. That's what you get by default when you create an Arnold AI standard surface. When you add in anisotropy, you usually turn it up to 0.9, 0.95, somewhere around there. I usually try to avoid 1 because I find it gives me some artifacting when I go to denoise it and when you render. But feel free to try it. It's real simple. Turn it up. It will work. Then you have to orient the stretching highlight. By default, it will try and stretch it horizontally. For something like this, brushed metal, we want it to stretch vertically, so we have to turn it 90 degrees. Easy enough. Except in Arnold, it doesn't use degrees, it uses 0 to 1. Don't ask me why. Just to drive us crazy. Because engineers didn't feel like doing 360 degrees. Is it 0 to 1 is good enough? Everybody knows what, you want 90 degrees, it's 0.25. You want 180 degrees, it's 0.5. Just half it. Honestly, it's not that hard. You want to rotate it 90 degrees, 0.25. That is 1/4 of a rotation if you go in 0 to 1. If you rotate it 180 degrees, all you're doing is flipping stuff around, so that's not really going to work. If you do 360, you're going to be right back where you were. You want 90. That is the common rotation. So I have 3 different metal materials here on these objects. This one is the default 0 anisotropy, 0 rotation. This one, anisotropy was added, but no rotation. Notice how it kind of stretches the highlights almost to the point where it's almost removing some of that roughness. This one, though, has anisotropy and it's rotated, and I'm getting that nice stretched highlight that I have. So brushed metal, anisotropy 0.9, 0.95. Depending on where your highlight stretches, most of the time it's going to be 90 degrees. Rotation 0.25. As long as you've got metalness in there, you've got the right amount of roughness, you should be good to go. Now, getting the right type of metal is going to be something we'll deal with in a bit, because that's going to be adding a little bit of gray for the most part in the base color and also the specular color. All right, does that make sense so far? All right, got a couple of resources for you, as I mentioned earlier. And I mentioned a little bit yesterday. We've got the standard surface user guide for Arnold here, which will take you in. And basically, if you go down here, it will show you all of the different sections of the material. So if you want to learn about specular, you can kind of click on that. And that'll tell you what the weight does, what the color does, what the roughness does. So really good use. This next one, the refractive index database. We're going to talk about this more when we come back from break, because this is how we're going to kind of find out the type of reflectivity that metal objects get that we can then use in Arnold. So like silver, what we want are basically the reflective index of how silver reflects light back. So silver, we know, or white metal, is going to be some kind of gray. You come down here to reflectance in 0 degree right here, it's going to be almost 1. That means when you look at it directly, the value is going to be 0.987, which is almost pure white, but not quite. So it's going to be a really bright white metal. You have to figure out, well, how does it reflect? What's the reflectance index at 90 degrees? Put in 90 here. This is a little return button. Notice most objects at 90 degrees are going to have a really high reflective index, which means your value is going to be on pure white, just like the default. Now, change to another material. Let's pick, well, one of my favorites is titanium. So titanium, which is very similar to stainless steel. They don't have stainless steel in here, but titanium. So take a look at, let's go back to the 0 degree reflectance. Notice that it's almost half what silver is. So it's a lot darker gray than silver, but yet at 90 degrees, it's still super reflective, all bandwidths of light. Now, this gets interesting when we start dealing with like copper and gold. And this will make more sense because that little demo file I have, we're going to be playing around with different materials, and we're going to try and make these different materials just so you can see how they work. But copper, where are we? Copper, here we are. So copper, it's like 0.755. So it's like 3/4 of the way there to be in white. For 0, 90, still going to be 1. But we need to add the color into the base and into the specular color in order to get that orange look. So metal actually has color in the specular, well, red metal has color in the specular color and also in the base color. Now, granted, take a look at the values here. So the color for the specular is going to be super light because the value is at 1. But at 0 degree, it's going to be a little darker. It's going to be a darker shade of that copper color. Sounds a little confusing, I know, but it'll make a lot more sense when we actually get in there and do it. But this has a whole bunch of other stuff. Some software packages will use what's called the refractive index and extinction coefficient to build metal materials. Arnold chose not to go that route. Arnold chose to use reflectance, and we plug color in manually. Now, there are some pretty interesting versions of copper, gold, brass, bronze in Arnold's website. Well, whoops, wrong one. Arnold, here we go. Metalness. So let's go to base. And here we go, metalness. So they're going by RGB colors 0 to 1. So for copper, there's your base color. Notice your base color is a lot darker than your edge color. Think of base color as 0 degree, specular color being your 90 degree. That's your edge color. So gold, base color is going to be a lot more saturated and a lot darker than the edge color. Now, personally, these are okay, but I prefer to actually sample the color off the reference and then adjust it based on the value that I find in that refractive index, and I'll show you how to do that. All right, now, when we start rendering this stuff out for today, when you render, your scene may look great. You may have enough camera AA, you may have enough diffuse samples, but you may see noise in your shiny areas, the specular reflective areas. That's where we're going to have to start increasing the specular samples in the render settings. So just like the diffuse, 2 and 3, that's preview quality, 4 is kind of medium, 6, medium high-ish, 8, high. Just be careful. Don't forget that specular is also multiplied by the camera AA. And it can become pretty unruly. And as we add materials into our scene, our render times are going to go up. Because now we're not just dealing with flat. Now we're dealing with different kinds of reflectivity. We're going to have glass, we're going to have metal, we're going to have plastic, we're going to have, you know, wood and wall. Anything that you've got in your scene, especially outside. You're going to have grass, you're going to have old wood, new wood, concrete, asphalt. All right, questions? All right, well, it's a good time to take a break. So come back at 3 o'clock. And that should give me enough time to get this recording out and up on the website. And we'll pick up and we'll start doing some demo together so you guys can figure out how this stuff works. All right, I'll see you guys back here in a little bit.